So welcome everybody. This is the second edition of I Can Believe It's Not Better monthly seminar series. And I'm delighted to today to introduce our speaker, Sebastian Nowozin. So Sebastian is a researcher at Microsoft Research in Cambridge, UK, and he's currently leading the machine intelligence research team. So his research interests include probabilistic deep learning and applications of machine learning models to real-world problems. Today, Sebastian is going to talk about why he can't believe Bayesian deep learning is not better. So Sebastian, all to you.
Yeah, thank you so much, Melanie, for the nice introduction, and also thank you all for attending. And I hope I can live up to the expectations that you have. This is a bit of a different talk, and I really liked the format of this series, which is to maybe slow down research a bit, to reflect a bit, and reflect on multiple levels, right? On the concrete research problems, but also on the higher level of maybe the research practice and how we got into a certain state, and maybe how we can unblock further great research in the future. So I do appreciate questions during the talk as well, in case you have. If you have deep philosophical insights to share, maybe we can do that at the end. But if you have some questions on a precise slide and so on, then we can do that during the talk. And it's a bit of a personal talk as well. It will tell a story, and I don't know if I'm a good storyteller, but you can judge me afterwards. So I would like to start with basically what I would think it was a majority position in the Bayesian deep learning community a few years ago. And let me see if my slides work. So yeah, they should work. So this is me around late 2018. I'm excited about Bayesian deep learning. There was like already 4 years of work in the field, a lot of interesting papers, technically interesting. And the main angle here is it's incredibly intellectually appealing. And I want to tell you first kind of like what I saw as the canonical view at the time and what was very appealing to me. So first of all, deep learning had a major success back then, right? Since 2010, 2011, deep learning has been hugely successful. And surprisingly, deep learning based on supervised learning using the log likelihood has been very successful. So even that class, which were covering 90% plus of successful deep learning applications. So if you use a cross entropy, if you train an image classifier, a language model, autoregressive language model, all these applications, machine translation, they were trained mostly on the log likelihood. And so that's kind of appealing as a person that looks for principles in machine learning, right? Because, there's a likelihood principle, there's probabilistic modeling in general. And the kind of simple picture to understand this is we have a very complicated parametric model, deep learning, right? We have an initial point, and then we have an iterative optimizer that does maximum likelihood estimation, right? And so that's kind of the basic way to how I guess many people coming from a probabilistic graphical modeling viewpoint understood deep learning at the time. We have efficient stochastic optimizers for log likelihood objectives. And of course, it's a difficult optimization problem. Initialization is important, it's non-convex, the learning rate choice is important. And people have done a lot of work to understand how these choices are important. But basically, at the end of the day, it's kind of maximum likelihood, right? That's how one can see. And widely successful as well. And then based on this, right, it's very easy to make the connection. Hey, if maximum likelihood works well, our experience in graphical models, in probabilistic programs, has been that if we go for maximum likelihood to a sound Bayesian approach, right, so Bayesian approach being the prior and the likelihood, we can reap benefits, and the benefits I will tell you about now. So it's incredibly appealing, right, to say there is the Bayesian approach to supervised learning. We have a prior over the parameters, and essentially the way we make predictions is not using a single model that we estimated using a parameter, but by an ensemble of models. And the ensembles of the model is based on a combination of single predictions weighted by the base posterior given a data set, right? So this is a weighting function over models. When the model agrees with the data that we observed, the model is given more weight, and when the model disagrees, it's given an almost zero weight. Right, so this is kind of an intuitively very appealing perspective, and I think if you read any paper from 1993, Van Kamp and Hinton paper, to David Mackay's work, to Chris Bishop's early work on Bayesian neural networks and so on, this is kind of the default perspective, right? And it's incredibly appealing. And the aggregate model, the ensemble model obtained by this particular Bayes procedure is called the posterior predictive. And so why would this make sense? Here's a graphical picture. So if you're not too much into equations, I have a few equations on my slides, but it will be light on equations. Let's say I have a regression task. I have a few data points here, right? And let's say the model that I build is a heteroscedastic normal model. So I predict the mean and I predict the variance. And then I say for my given input X, right, I have a normal distribution and a mean and a variance, right? So this is one way to build a model. And now let's say I estimate, given on this small set of data points, I estimate this function. And what I can do then with maximum likelihood, if I have a parameter obtained here, θ1, I can look at the mean and I can look at this sigma function, right? And I can say, hey, this function looks like a reasonable interpolation and extrapolation of the data. But maybe if I repeat this procedure with a slightly different model, or even just with the same model and a different initialization in the case of deep learning, right? Because it's non-convex, there's some complicated dynamics, I obtain a different fit. And the fit is equally good. As far as I can tell from the data, it's an equally good fit, right? And the way I would tell this is the optimization objective, the maximum likelihood objective is both very small in this case, maybe even close to 0 for deep learning for most of our models, right? So this is really dissatisfying, right? I have one model, I have another model, and they all agree with my training data, but they agree outside of my training data, right? And to capture that, right, basically I have many models that fit the training data equally well. And so the Bayesian idea here says something very simple as well, use all of them, right? And the models that have good agreement with the data, they are more strongly weighted, and the models that have less agreement with the data are less strongly weighted. And so if I do that, I obtain something very satisfying. I obtain close to the data, right? In this case, it's a 1D example. And of course, if something in 1D works, right, it may not work in high dimensions. We know that. But in this case, right, this is actually what usually happens, right? Far away from the data, there's lots of disagreement. And so if I now predict using the posterior predictive, using this combination of models, well, all this disagreement is captured in the variance, right? And all the agreement with the data, the variance is small and consistently small for all the models. So the variance is small there. And this is intuitively very, very pleasing. And I get nice properties as a result. So if I have a point that is similar to my training point, right, I get good estimates and low variance estimates. And if I have a point outside my distribution, well, there's lots of disagreement here by different models. So I get disagreement, right? And I get I have a signal in terms of the predictive uncertainty that this is bad. And this has been studied from various angles. There's recent studies as well that examine particularly the out-of-distribution properties of Bayesian deep learning. Lots of interesting good work. I just cite 2 works here. This is not like an exclusion, but basically there's a lot of interesting work happening in that space, studying precisely these properties. But the basic hope is that we get all of these things. And so to capture this viewpoint from a few years ago, I would say the canonical viewpoint is, well, SGD is kind of doing maximum a posteriori estimation, right? So you basically regularize maximum likelihood. And if MAP works, surely some Bayesian posterior predictive is going to outperform MAP, right? So this is kind of the picture you can find in the third chapter of McKay's book or something, or even like in Chris Bishop's PML book, right? MAP is a simple approximation to the base posterior. It's a point approximation. And then there are variational approximations. And then there is a full base posterior. And of course, one is strictly better than the other in terms of predictive performance, right? So that's kind of the narrative, and it's very intuitive for the reasons that I mentioned, right? It captures this variation that is artificial. Well, and then there are all the benefits that we hope for, right? So surely by having a posterior that captures all of this, we could hope to be more sample efficient. So the model could learn faster, right? Because the uncertainty would collapse where there's a lot of evidence, and it would remain vague where there's no evidence, right? Bayesian deep learning will have better uncertainty estimates for the reason I've shown, right? Better out of distribution uncertainty, et cetera, et cetera, et cetera. Right? And I think that's kind of the compelling thing that lured me and many other people into Bayesian deep learning. And then the only caveat is, well, inference is hard, right? Inference is always hard already for graphical models. And now, inference for Bayesian deep learning is maybe even harder, right? But basically, let's say we could do inference, right? We have a wonderful goal here, right? We just need to crack the inference problem, and we would have an amazing way to use the best of deep learning and sound probabilistic reasoning to get really good Bayesian deep learning models. And so with this, when I joined Google a few years ago now, I thought, okay, that's a problem that is interesting. That's a problem maybe that's ripe for a concerted effort to really make the Bayesian deep learning working. And so I embarked, in hindsight, maybe naively, on this. But I think sometimes it's good to take an extreme viewpoint and believe in something, and you may either succeed or you may get the evidence that that it's not as simple as you thought it was. But when we started on very simple models, so we basically had from the very beginning, me and a few other people in Berlin in the brain team then, we had the goal of really making this more widely accessible. So we basically started with Keras models and added a library around Keras. So you can basically turn any Keras model into a Bayesian deep learning model. And so we took the simplest Keras example test case, and there's a couple of small innovations that we had to do, but basically the initial results look very promising, just in line with what I've shown you. This was a super small model. I think it was a Linnet 5-layer. It's not deep learning. You wouldn't call that deep learning now. But basically we had a SGD validation cross entropy loss here, and this is a typical fitting and then overfitting behavior. And then we have an approximate base posterior represented by, say, 20 samples. And the way we did draw this curve, I don't have the original curves, unfortunately, but basically we invented a method whereby, you have a Markov chain that runs through the parameter space, and we would have an unbiased sample of the second half of this Markov chain. So while this Markov chain runs, right, after a million steps, from the last half of the steps, we would have an unbiased sample, right? And an online way to draw, and there's a technique called reservoir sampling to do the same for a whole setting. And we basically had like a fresh reservoir method that would draw only from the second half. So now you can imagine the more you sample, the more the second half of your trajectory would converge to the limiting distribution. That's a property of the Markov chain having the right stationary distribution. And basically there was a monotonic decrease. It was better than SGD, and we never saw overfitting. And so this was super encouraging, and really, basically, we were very excited about this result. Right? So then at the time I said, hey, we need kind of, we need to rally to the cause. We created a little laptop sticker that you may have seen, right, of a referent agreeing with this approach, and really some excitement and momentum around this. And maybe let me talk about bit more about the approach that we took. So we basically did stochastic gradient Markov chain Monte Carlo, which at the time was already becoming more popular because it was very difficult to get variational inference to work on Bayesian deep learning. And but basically how it works is just like with optimization, but you add noise in every step, and the noise is chosen such that you basically you don't converge in as a point mass, you converge in distribution, and you converge in distribution to the true posterior. Now it could take very long. It's not necessarily efficient, but it's very close. It's basically SGD with noise. And you take samples along this trajectory, and these are your approximate samples from the posterior, right? And then you can approximate this posterior predictive object using a finite set of samples, say 10 or 20 samples. So that's a basic construction. And it's basically conceptually as simple to operate as stochastic gradient descent. Now, at the time, this didn't hold exactly. And let me tell you about one small innovation, which I think is perhaps quite crucial if you're interested in these methods. So all the stochastic gradient MCMC methods are derived from the Langevin flow, or so-called Langevin dynamics, which is a physically inspired dynamics of a flow driven by a gradient. This is the gradient of the log likelihood objective, plus a momentum term, which is coupled to this parameter space, and plus some noise process, which in this case is a Brownian motion process. So I don't have time to explain stochastic differential equation, but either if you know stochastic differential equation, you probably know the Langevin dynamics already. And I want to really emphasize that basically it's an equation here. In order to implement it, you need to discretize it in time, and there are some couple of choices that you need to make. So you have some object called the mass matrix, you have some parameter, the friction coefficient. These are all physically inspired quantities with certain units, and in particular also in this case a temperature parameter. That's the amount of noise that you add, and that will be critically relevant in the rest of the talk. So the problem is you need to discretize these dynamics in order to make them implementable. Just like a continuous gradient descent flow would have to be discretized to get an actually implementable gradient descent procedure. And when you do that, you have a step size h. And the problem is the step size h is not a commonly understood quantity like the learning rate in deep learning. It has a different scale. And that makes these methods slightly difficult to operate. So you have basically two additional parameters, this gamma parameter and the step size parameter. And that's the key difficulty. You could say, actually, that's easy, but choosing a learning rate in deep learning, there's best practices. You can do that relatively straightforwardly now. And some methods are more robust. Say Adam is more robust to the choice of learning rate than SGD with momentum. But for these SDEs, it's actually quite critical to choose these parameters correctly. And so what we did here was, is to show that you can basically define a bijection between parameters that you know about, for example, the learning rate L and the momentum decay beta. These are the choices you would do in SGD with momentum, and these step sizes and friction parameters. And when you do that, you can show that you can basically reduce the stochastic gradient MC methods to stochastic gradient descent methods with momentum. Exactly. So it becomes exactly this method. And what this allowed us to do is literally just replace an optimizer with the same parameters as with SGD with momentum, and the code would work, and the trajectory would initially look the same. So that's kind of the statement of universal applicability. Like if you can run SGD, you can run this SGMCMC method. And there's a lot more interesting small innovations that we did based on a great book, 2015 textbook by Ben Leimkühler on molecular dynamics, which is a very different physical simulation system. But basically, we read this book very carefully, me and Kevin Roth, a PhD student at the time in ETH, and we shake that book, and a lot of interesting methods fall out. And there's one more I will mention later. But basically, yeah, so I just want to mention that. And it's a very small innovation that turned out to be really important to allow us to apply these methods to larger models. Okay.
Sebastian?
Yeah.
Sorry, there is a clarifying question. So Luhan Wu asks, is there an interpretation for friction parameter?
There is, if you ask a physicist, I'm not a physicist. If you ask a physicist, they will tell you the friction parameter has a unit of 1/time. So 1/second, that's a unit of the friction parameter. And it's basically the strength of the coupling to the noise source, to a heat bath, the physicists would say, with the process. So for any positive value of gamma, of this parameter, of this friction parameter, the continuous time SDE has the right limiting distribution in terms of the parameters. But it may mix differently. The mixing speed may vary. So there is kind of, you want to choose these friction parameters so that you have a good mixing speed in the parameter space. And how to do that, I think depends very much on the application and the stiffness of the system and other kind of things.
Okay, thanks.
Okay, so now I told you a bit about the method. I told you about the excitement. And then this is the work that we then did in 2020. And basically, this is where the second part of the story starts, the slightly depressive or frustrated part of the story starts. And so basically, when we then applied these methods that we had developed to realistic models, and realistic, still small scale, but these were like real, the standard ResNet 20 implementation that was included in Keras. So these are kind of like, again, standard models. We didn't modify these models at all. The curves look different. The curves looked like this. And this was a shock to us in a way. We didn't expect that. So first of all, the model underfit. We never got, the posterior predictive never got to the level even of SGD models. And moreover, we saw overfitting. Nobody told me that Bayesian models can overfit. I mean, I knew it at the time already. I have a blog post, actually, if you want to check that out. But there is kind of this standard narrative, or like I would say the naive narrative. Most serious researchers in the field, of course, know it's a bit, it's much more nuanced, right? But there is this narrative that Bayesian methods cannot overfit. It's completely wrong. And not just in this example, you can have very elementary examples where this is the case. So, so in that case, we observed it in our models, and then we went back to the drawing board. We need to understand this. What happens here? Where is the source coming from? And the result of that is an effect that we identified, which we called then the cold posterior effect. And basically, this is the first page of the paper, but basically it's all encapsulated in this plot. We have this temperature parameter, and the temperature of 1 corresponds to the base posterior. And it turns out for the base posterior, the performance is worse. In this case, it's classification accuracy, I think, or yeah, on CIFAR 10. So classification accuracy on the, let me see, on this temperature 1 scale is worse than SGD. And that was unexpected for us. But if we decrease the temperature, actually the ensemble of models in this cooled posterior, right, actually improves eventually over the SGD model. And that's, again, not necessarily clear why that would be the case. So, so I will spend some time explaining the effects. Probably I will skip over a few slides, given the, I spent too much time talking about the larger context. But basically, so we have this plot that you have just seen. It also holds for cross entropy. And we also did it on an autoregressive model, so a very different model where the parameters are coupled. And again, the same effect appeared. And so the posterior of our parameters here is temporized by a capital T parameter, the temperature parameter. And for temperature smaller than 1, basically you weight the likelihood strongly, or like you sharpen the posterior, it becomes less dispersed. And yeah, so this is where my frustration starts. This was early 2020. I thought, oh, this whole direction of pursuing the Bayesian dream and Bayesianizing the whole of deep learning and building frameworks where people can just change one line and they benefit from the Bayesian technology, right? And finding good applications that go all the way to really demonstrate the value in the field, which was also, by the way, interesting because as a Bayesian deep learning person at the time, I thought people want better uncertainty. And if you talk to people that work on applied domains, they say, yes, I want uncertainty. And then you ask, okay, what are you going to do with this uncertainty? So I guess I could. And they don't even know, most of them don't even exactly know what they want in an uncertainty, right? Whereas what we saw initially was an improved predictive performance. Everybody understands improved predictive performance. Everybody wants an improved predictive performance. So I saw that as the clearest way to convince people of the value of Bayesian deep learning, right? If you can get better predictive performance with the same data set, or you need a small data set to get the same predictive performance, right? Everybody would cheer you on and buy this technology in a way, or like take this technology, right? So here's where I kind of was depressed. And so the first thing that we did is we looked at the literature, right? Surely, I mean, this seems to, either we made a simple mistake in our implementation, or this must have been, I mean, Bayesian deep learning had 100+ papers at the time already in the field that were well cited. Surely somebody must have observed that. And so what we found is actually in the few papers that applied stochastic gradient MCMC methods, they all also temporized the posterior. Actually, in 2 cases of the 4 I list here, it is an implementation mistake. So we went into the actual code bases and reverse engineered the equations from the code. And sure enough, there was, for example, a division by the square root of the sample size happened in parts of the code, and not intentional. I think it's just, natural implementation mistake. And then these models work, and then you say, hey, my model works. Surely it must have, yeah, I have a good method, right? So all of these happened by basically, 2 of them happened by implementation mistakes. 1 of them happened by, using data augmentation and then reducing the effect of that to prevent overcounting. And then we also looked at variational Bayes, and sure enough, people were used to weighting the KL term in the variational Bayes approach, right? And it has a very similar interpretation to temporizing the posterior. So we make that precise in the paper as well. But basically, in none of the works that did serious experiments, we found any evidence that anyone has ever done Bayesian deep learning successfully with a temperature of 1. And that was a moment, and when we realized that, it was a moment, okay, this is interesting. Let's try to understand that effect more. Let's shelve the original plan of Bayesianizing the world. We need to understand this, right? And also, we just started to socializing, talking to some people and mentioning this observation. And then the reaction is also interesting. So I want to, this was 2020, so this was kind of almost 2 years ago now, right? But basically, there's kind of the denial reaction where people say, oh, there's not a problem. It's still fully Bayesian. And they have an ad hoc explanation why it's fully Bayesian. Maybe, we can just we can just add an exponent to the likelihood or something like that. And that's not true. And there's an appendix also in the latest version of our paper that, for example, picks some of these arguments apart. Then there is the other reaction to say, oh, surely that's the approximate inference to blame, or surely it's because the model is misspecified, or surely it's a wrong prior. And it's a single reason, and I confidently can tell you what it is, right? And I think that's also not scientific, right? Especially it's not Bayesian. I mean, if you don't have evidence for it, right, how can you be so certain, right? It's a hypothesis that you can test, right? But putting it as almost a fact out there. And so there's another third and more positive reaction. A lot of people, actually probably a dozen studies and papers have looked to try to understand this effect further. And I think that's the most productive way. And there is a summary of in a recent paper of Lorenzo Noki, and I also was involved in that. There's a summary of all the work that had happened until December last year in this space. And so the idea is that So let me probably skip over a few next slides. So the 2020 paper is structured around examining different classes of hypotheses. And I probably will only talk about inference accuracy and skip the remaining ones of these hypotheses. I have slides for all of them. I could talk about all of them if there are specific questions. Maybe I will talk about what has changed for some of these hypotheses. But basically, one of the first hypotheses is, well, do you do accurate inference? Maybe everything is okay, it's just the inference, right? Because that's one of the key challenges. And I have to convince you that I have made progress in these. Otherwise, it's fair to say that, you know, approximate inference is really hard. And so we did our best to do inference accurately. So we had a couple of different hypotheses there on what could be broken in the inference. And we developed two diagnostics, which, as far as I know, haven't been used before, certainly not in Bayesian deep learning, but we basically just imported them from the field of molecular dynamics. And these are, there's a universal way to construct so-called temperature observables from the state of a system. And we constructed two of them that were present already. There's an infinite set. For any differential function, you can construct one. But basically, there's a kinetic temperature, which is maybe familiar to some people in the HMC field. And then there's a thing called the configurational temperature. And what these two quantities have in common is that if you sample accurately, then the mean of both of them will be exactly the target temperature that you have. Whereas if you have sample inaccurately, typically the temperature that you estimate is higher than the target temperature. So for example, the discretization adds it's a source of heat, it's a source of noise in the process, and that lifts the temperature of the system. And so when we run this diagnostics, sure enough, on the first set of models that we have, this is again a ResNet 20, and every one of those bars is one block of parameters in the model. So this is 20 layers. There's convolution kernel, bias, convolution weights, bias weights, convolution weights, bias weights, and at the end there are some linear weights. And the bars, the green or red bars, are the confidence intervals where the temperature observables should be in, right? And because they're estimated and we know the sampling distribution, we can basically write these confidence intervals where they should lie in. Or it's a 99% the highest probability density region of the true sampling distribution, if we were to sample perfectly, right? So by basically out of these 132 data points that I show here, almost all of them, 99%, should lie within their box. And then the box is green. If all of them lie in the box, it's green, right? So this tells us our inference is not accurate. And then basically we added a clever preconditioner, which improved the situation a lot. And then we also removed the source of discretization noise by following practice from prior work of Zhang et al., Ruchi Zhang, and others, to basically follow a cosine schedule. And sure enough, at least by this diagnostic, we can say that our trajectory is really seen through this diagnostic satisfy all these temperatures well. And we had other tests as well here, and basically we could rule out these hypotheses to some extent. We can never 100% guarantee that we do 100% inference correctly. There's a retake on that. So Pavel Ismailov and others looked at doing HMC runs, very expensive runs, and they could remove this cold posterior effect if they also turn off data augmentation. So it's a great experiment and really valuable for the community. But they conclude that approximate inference is to blame, and I'm not sure I fully buy that for two reasons. So one is already prior work of Ben Adlam and others has shown that cold posteriors even arise for exact inference in Gaussian processes, right? So it can't be inference there because it's exact inference, right? And also there's another paper. Let me just skip here. There's an interesting thing about likelihood functions. There's data augmentations. People have independently reproduced the cold posterior effect if they use data augmentation. And also the form of the prior is important. There's additional studies nowadays where basically the cold posterior effect becomes stronger as the prior has more influence. So if you have fewer data, the cold posterior effect is stronger because the prior has more influence. So the prior is also implicated. So data augmentation is implicated, the prior is implicated. People have implicated data curation. So for example, CIFAR-10 is a highly curated data set. So a lot of different, let me see, just conclude that. Basically, a lot of different reasons have been independently implicated, and the cold posterior effect has been produced as a consequence of careful experiments examining only one of those facets. So the prior matters, data augmentation matters, the data level of data curation may matter. Inference accuracy has an influence, but it's unclear how strong compared to the other effect. And the problem is, based all of this on our work and the following work, there's not a single reason that was identified, and therefore there's also not a single simple fix. And I think that's kind of a bit humbling, right? I would have hoped that some clever person comes along and has a clear insight, and there's one fix, and Bayesian deep learning works now. It's not the case. Now, where does this leave us? Is it fundamentally broken? Maybe not. We can just use a smaller temperature, right? It's an additional hyperparameter. Maybe we should be very happy with that. Or we can open the definition of Bayesian posteriors in general and say, like, any ensemble model is now Bayesian. Let's just define it like that, for example, right? And then, ensemble models work. We have deep ensemble methods. We have other ensemble methods that are maybe more efficient, accelerated ensembling methods, and so on, right? Maybe we should all be happy with that. But in my heart, I'm still a Bayesian. I think I would like to understand the origin more, and I would like to design better methods that are really Bayesian in principle and really to the true sense of the word, prior times likelihood, and there's a posterior, and not in a way with a relatively ad hoc that, Ferenc Husa in his blog a couple of years ago, he had this joke, any model that works is somehow Bayesian anyways, right? So basically the Bayesians absorb all the models that work. And conceptually, that's kind of true, right? If you agree with the data, that's the models you should go with, right? And the Bayesian approach captures that. But I think there's a sense of purity, I think, to the approach that is worth preserving and understanding it. And maybe there's a deeper insight still waiting there, right? And given that insight, we can improve the models. So now I just want to say I'm kind of recovering now from my disappointment with Bayesian deep learning. And I want to,
Sebastian?
Yeah.
Sorry, I think Andrew Wilson wants to ask a question. Andrew, do you want to?
Yes, please, Andrew.
Hi, Sebastian.
Great to see you on the talk.
Thanks. Yeah, I'd like to ask a question about some of the claims that are being made. So it seems like a running theme is that because we're doing tempering, that Bayesian deep learning doesn't work. But as you noted, some papers, including ours, like a paper on what are Bayesian neural net posteriors really like, notice that when you remove data augmentation, t=1 actually provides near optimal performance, not just in CFAR10, but also in IMDb. I noticed one of your follow-up work said, well, it just happens in CFAR10. We also noticed this for IMDb. And in many other experiments, we've also noticed this, suggesting that, well, augmentation might not be the only reason that we're doing tempering. It might be largely an artifact of tempering. It could also be the case because augmentation and other things we do can soften the likelihood that a tempered posterior might be more Bayesian than a non-tempered posterior. For instance, many of the benchmarks that we're considering, like CFAR, actually have no aleatoric uncertainty. And so by doing something like tempering, we might actually be doing a better job capturing that. So it seems to be a strong claim that isn't particularly argued that by doing tempering, somehow Bayesian deep learning hasn't worked. And it seems that in the last 4 years, especially since 2018, I would argue there's been a lot of very promising empirical progress in making approximate Bayesian inference procedures faster, better performing, seemingly better calibrated, and so on. You noticed that you pointed out some issue with this sort of an argument about kind of like how you're sort of just changing your likelihood or something like that. I honestly think that sort of misses the point that was being made. The point was really that this has a similar effect on the predictive distribution to something like the noise variance when we do Gaussian process regression. And there were also a lot of other points. This is sort of like, 3 sentences and a few pages actually that was discussing this issue where it was shown, for instance, that the prior being overconfident seemed to mostly just be an artifact of not having a good signal variance, for instance, in the distribution over the weights, and this could be very easily resolved, etc. So I guess the question is it really fair to say Bayesian deep learning doesn't work because we're using a temperature less than 1, when a temperature less than 1 might actually be more Bayesian than using a temperature of 1, when other things are happening, like data augmentation, maybe a misspecified likelihood, and so on, that can be partially corrected by doing tempering. And in general, all of our models will be misspecified, and temperature scaling is one way of trying to help with model misspecification. Surely it's not the best way, and there are other things that we ought to be exploring, like changing the likelihoods and so on. But I am worried that maybe we're just holding Bayesian deep learning to an impossible standard here. If it somehow doesn't seem completely pure, then it doesn't work.
Yeah, thank you for your explanation and for your nice question. And I think, you know, we have discussed this point many times in different settings, sometimes in heated exchanges, and I do appreciate intellectually rigorous exchanges on this. And I think your work argues what you just said in a coherent and nice way, right? There are some technical precise disagreements that we have, right? But let me come to your question. So I think, you know, in general, I'm very happy with ensemble methods with a goal of more efficient methods that learn ensembles that are, you know, maybe inspired by the Bayesian approach and so on. And I'm not a Puritan about the word Bayesian, but I do think that, you know, the Bayesian approach is very logical. And if you want to preserve that coherence, right, then it is worth thinking about how to either map certain things in the Bayesian thing, right? So how to interpret, for example, data curation. So Lawrence Atchison had a nice paper on what a Bayesian model for curation would look like and how estimating that would correspond to the curated setting and so on. I think that's a fruitful thing, right? To basically include certain effects. We had in our original work, we had this Jensen posterior thing going. I don't know how, I mean, it hasn't produced a practically working method, but it was trying to accommodate certain deviations from the likelihood principle into the Bayesian deep learning framework in a coherent way. I think that's a regime, right? Building practical methods like your SWAC method, right? I'm also a big fan of like practical methods that are efficient, right? So that's all good, but we do have technical disagreements. And so, for example, you know, you could there's a precise technical question about like, can you temper just the likelihood? Can you just is there an equivalent model that correspond to the temper and setting that works, right? It's an equivalent way to write down that. And the precise technical answer is not in the general case, right? And I mean, that's where we have technical disagreements, right? And where I just think, you know, one has to be a bit careful there, because this is kind of true or false on an equation level, right? This is not.
I agree with that. I think on one hand, it seems like there's sort of 11 points that are being made in response to the cold posteriors effect. And in one of them, maybe there is a technical debate and maybe we're dwelling on that a little bit. I actually agree with your perspective on that one point.
Okay.
I don't think it necessarily means that Bayesian deep learning doesn't work. And I think, you know, this thing you proposed about having another class and so on, that might be a reasonable interpretation if we're sort of looking at points that might not belong to any class. And I do think that probably we should not be using the softmax likelihoods. But at the same time, I think given that there are many parts of the model that are unspecified, it could well be the case that tempering is actually a more Bayesian sort of approach to inference than just using a t=1 and pretending that the model is perfect.
Yeah, I'm not sure about that. And the reason why I'm not sure is, right, tempering is a one parameter thing, basically taking the power of some object, right, or multiplying the logarithm of that object, right? And why is that the natural thing, right? There is some, I mean, I know of some classical works that examine for small parametric model that make precise arguments, right? But why is tempering the right thing? Why not any other monotonous map of the likelihood? Right? Why should we stop at tempering? Why not parameterize a monotonic map of the log likelihood function, right, and map it through there? Right?
It's a simple and effective approach. It's not the only approach. It helps soften the likelihood in the presence of augmentation.
Correct. So now I agree. I fully agree. Right? It's effective, right? And that makes it interesting, and we certainly makes it interesting to study that, like almost from a scientific point of view, understanding this phenomenon, right? And in that light, I mean, the HMC work is great, right? At some point, we have to say, though, you know, how do we specify prior knowledge about the problem, right? And so if I just add a hyperparameter and it's tempering, or if I add now another parametric transformation of the log likelihood, or some other kind of thing, right? At what point can I really say I'm Bayesian? And maybe, you know, if I just remove the word Bayesian, you know, whatever works, everything's on the table. That's the beauty of deep learning, right? We can all explore building blocks, we can all explore models. If you show something works, it's great. I think
there are many things you could do, but we can keep going if you like.
Yeah, sorry, Andrew, Sebastian. And maybe would it make sense to continue with the presentation and maybe
I mean, I'm almost, let me see.
Thank you.
Yeah, but I do understand. I mean, that's maybe where we can agree on, Andrew, right? Is given all these studies and all these experiments, right? There are still many open questions on this effect, and understanding that further and building on methods that are based on this understanding, right, has potential in the sense of providing more effective methods that are more practically useful. And I think that is a good goal beyond just understanding this effect. Let me see.
I just don't think we should have an impossible standard for what it means to be Bayesian. And I worry that we're getting there. Like, I feel like there's a spectrum. We're moving closer to the Bayesian ideal as we improve the fidelity of approximate inference, but it's not binary.
But you see, if the gold standard is the Bayesian approach and the measure of progress is how close we are to the Bayesian approach, I think we have already lost it. Right, so that's kind of the frame of reference problem, right? That I was alluding to, right? If we chase
I
this
disagree
rainbow,
with that.
we
I
may
mean,
never
we
get
do see evidence.
Sorry, I will execute my power of moderator here.
Thank you. Thank you.
Sorry, Andrew, if that's okay, let's
let us recover here. And by the way, I'm no longer vested in this research space anyway. So you know,
perfect slide.
But yeah, let me talk about this. And this is maybe this is maybe even more opinionated, right? So this is kind of now a value judgment, and there's no right or wrong in the way here, right? You can assert a different perception of reality here. But I think one of the questions is, honestly, you know, Bayesian deep learning started, you know, around 2014, 2015 to be revived. It was, of course, has a longer history, right? And yet it took this paper, right, in a way to bring this problem. And now your question is it a big problem? Is it a small problem? Maybe it's not a problem. Maybe it's, but it took a while for this problem to come into sharp focus. So it took at least 5 years, from my perspective, for this problem to surface. And that's a bit shocking, because there were like large workshops in the community with, you know, hundreds of people working in the area, 50 plus papers per year published in the space. And I think one explanation is simply that the whole Bayesian deep learning community was disconnected from actually all the main progress in deep learning, and from, in that sense, also from relevance. So there were tiny models, no benchmarking, an emphasis on methods, not results. And I'm guilty of this myself, right? I can get an ICML paper on a new type of matrix factorization variational posterior approximation family. That's technically rewarding. It's really interesting. I can show it on a small model that it does something, and I have a nice technical ICML paper, right? So, and similar examples. This is an example for myself, right? So I am not, you know, assigning anyone here thing, but we were driven by methods, by excitement about deriving nice methods, not about progress for real tasks. And I think that led to a drift, a disconnect of the Bayesian deep learning community. The positive thing there is there's a lot of progress here, right? So for example, the uncertainty baselines project and other projects which really put this on a more solid footing, and toolboxes which can be used. And that is installing some goals and metrics now, but the goals and metrics are also not clear. So what is uncertainty? How do we measure it, right? There was a huge gap in 2015 to 2020, right? What is OOD? How do we measure sample efficiency? What's the application to continual learning? All of these motivations for having better probabilistic deep learning models, right? They were not captured by metrics, not captured by relevant tasks. And then the third answer is maybe most opinionated. I think there is, you know, because we are caring about principles, we're caring about the foundations of learning as Bayesians, right? About coherence, about the advantages from a principle point of view, right? With it comes perhaps a certain kind of confirmation bias, and with it comes perhaps a certain advocacy. And I have observed that, you know, I hope I didn't fall guilty to this myself, but I think that's softened now in the last 2 years, certainly. And I think that's a very good thing. So that's just my opinions. The good news is, as I said, there's great projects on benchmarking, on tooling, studies of the challenges of Bayesian deep learning in general, and a more mature community overall. And I think we can all benefit from that. So with that, and thank you for the questions already, but I hope we have among the set of attendees, we have also many other questions. With that, thank you very much for your time.
Thank you so much, Sebastian. This was absolutely fantastic. I mean, I love also how you are making this seminar very special and different, like not only like just, okay, here's my new research paper. No, it's about like thinking, so about a very different, and interesting research questions, and pausing and like paying attention to these unexpected results, and then also very humble, no, trying to make reflections on how we're doing research. So that's actually the goals of this initiative. So yeah, thank you so much. Okay, so let's start with Q&A. And so everybody please put the questions on the chat. And yeah, so while people are gathering questions, so I do have questions myself. And I guess, okay, regarding the cold posterior effect, so in your work you raised there are different sources, right? There is not a unique cause for it. But I wonder, so there are like very interesting connections between them. And in particular, for example, if we think about aleatoric uncertainty, So it has been observed that as whenever there is overestimation of aleatoric uncertainty, then there seems to be a link or more likely the posterior effect observed. So do you think that maybe there could be some underlying, latent cause that actually, that there are many of these things can cause it, but maybe it's just that we don't understand what's going on underneath, and maybe it can be a simple explanation that still needs to be.
I mean, I hope, but as a Bayesian, I have an epsilon of probability mass on this event. So basically, I'm not aware of the results that you mentioned. I mean, I can imagine it, right? And I don't know. I think the key question is, in a way, right? We use deep learning because we want large capacity models, right? High capacity models, right? And this is fundamentally different from small parametric models with variables that make real sense in the problem domain, right? We don't care about the precise value of the parameters in most of the deep learning problems, right? So that brings unique challenges. So and these challenges should be embraced, right? Even like in normal deep learning, right? What's the effective regularization? What's the effective prior for these things? So I think this is all, it's all fair questions, right? But I think it's a very difficult learning regime in principle, and therefore maybe all of these effects matter. So far, we have seen in different settings this effect can be reproduced. I would love if we could somehow capture all of these effects with once. Maybe Andrew can construct a model where tempering is a latent variable, and we have a prior over the tempering, and it is all automatically by marginalization everything we have an optimal choice. Right? But I would love for a resolution that makes sense conceptually, formally, and resolves this and leads to practical methods. In the end, my filter I have enlarged my filter to just practical methods. I have no longer practical methods that have a sound Bayesian justification or something. I dropped that predicate for myself, but I hope others don't drop it and do good research in that space and come up with really good practical methods. But they need to live up to the standard of the larger deep learning community. It should not be constrained to some cozy intellectual space in a sub-community. I mean, new methods, maybe they get, really, really cool, interesting methods. They have a bit of extra, and Europe's rewards intellectual methods. So I'm not worried about, shutting those down. But I think eventually the community is now mature enough. They really have to deliver in terms of predictive performance, in terms of uncertainty quantification, and the more dedicated effort in that space. And I see these efforts picking up, right? I mean, Dustin Tran's work, for example, an amazing set of works. And people work on this, and this is good to see, and this should continue. Sorry, this was more like a long, winding answer, not really answering your question.
No, this is very good. Yeah. I guess, yeah, okay. I have another question, but I want to also let other people ask. So Kevin Murphy, he's asking if you actually could talk a little bit more about the model specification on the slides that you skipped. So maybe a few
Definitely.
minutes. Yeah.
Let me see, which slide is that? Did I have a slide?
And Kevin, feel free to unmute yourself if you have specific questions. Just go for it.
I didn't have one on model misspecification. I had problems on the likelihood function and how basically the typically used likelihood functions in deep learning, for example, using batch normalization, using data augmentation, using dropout are not Bayesian. But let me say something about misspecification. So the difficult thing with misspecification is, first of all, the definition, right? There is a very precise definition in statistics. So Halbert White wrote a whole monograph on specification analysis of parametric models, clearly defined what misspecification means, the very precise meaning. But we use it very loosely, right? We somehow, when we say a model is misspecified, right, we mean something different, and we take into account maybe the prior. In casual conversations, right, we say that basically the prior predicted probability mass doesn't really is nowhere near close in function space where the data lives. That's kind of like, I think, maybe how it's commonly understood, right? So we can have a lot of data, and it would be almost impossible, or is it impossible, to override the prior beliefs baked into the model and the likelihood function in the prior. So that's how it's commonly used. And so by that definition, any model is misspecified. Even the largest vision transformer applied to CIFAR-10 is misspecified, right? Because it's a very high dimensional space. We have a relatively small set of parameters, even if we have hundreds of millions of parameters. So that's not very useful as a practical definition, right? So I don't know what to make of it. So it's kind of a get out of jail argument. You can make always, you can say the model is misspecified. Yes, you're right, right? You're right. So what? So if we want to go that route, we have to be more precise what we mean. And we did this, for example, with the prior predictive checks. And then it really becomes a very quickly a very detailed thing. So for example, what we discovered is if in a ResNet model, right? There are ResNet variants, and say that if you download the standard PyTorch ResNet implementation, I think the standard PyTorch implementation, right? There are no bias terms in the first few layers. And if the TensorFlow Keras ResNet implementation has bias terms in the first few layers, in the first few ResNet blocks. And that makes a difference. It makes a lot of difference what happens on the prior predictive. So you suddenly start, now it's a more open problem. It really depends on the model and actually on the implementation of the model and on the initializers that you use, etc. Right? So I think it's not a very useful concept from what I have seen to think about misspecification, except from a theoretical, information geometry point of view. There are some very nice and interesting and clean results, but it's not very useful in deep learning, unfortunately. Maybe Kevin has a different opinion. Maybe it's in a new edition of your book. Is there a chapter on misspecification? I would love to read it.
Yeah, no, thank you, Sebastian. There is another question from Jan Altozar. He asked, do you have thoughts on posterior predictive across pre-training seeds for very large models like BERT?
Pre-training seeds of very large models. I can't say I have a full understanding of the question, to be honest. I do see.
Yeah, sorry, Sebastian.
Yeah.
I think I'm just struggling to understand the utility of posterior predictive distributions if you have models like GPT or like BERT that themselves take like a few hundred GPUs or TPUs and several weeks to train.
Yeah.
And then in order to get something like a posterior predictive, you need to ensemble over many different seeds of that pre-training process. Okay. And it's very, very hard to get like a fine-tuning confidence interval over those pre-training seeds.
Absolutely. And I'm with you on that, right? And it actually motivates, let me say the constructive answer to that is, right, that puts an extra emphasis on efficient ensembling methods, right? So things like swag, things like, taking just samples along the SVG trajectory and things like that. So methods that don't pay an extra overhead. And so when I, for example, talk to real, actually large deployment teams that deploy large deep learning models, right? They say, okay, actually, if it's slower than twice, if it takes more than twice as much compute and cost, actually, it's a cost of operating these services at scale, right? It won't fly. Right, so that's kind of like a hard criteria. Anything you need to do, the improvement needs to be really there, but also kind of within a factor of 2. So, I totally with you on that, right? And for example, there are things like the MIMO networks and other work that are very clever in terms of representing an ensemble of models more efficiently, so that computation passes can be shared. So you basically exploit the property of modern hardware to carry out certain computations at a sublinear cost, right? If you batch certain computations together, right? That's kind of the main way why a matrix multiply is fast on a GPU. If you can exploit these particular types, you don't have to pay linear overhead to get almost as a linear benefit from having ensembles. But yes, I agree with the fundamental point. And in particular, in these very large models, language models in particular, and also in the kind of Hugging Face paradigm of having large pre-trained models and doing fine tuning, right? What's the value of having a rich posterior predictive on the full parameter space? I totally with you on that, and it actually motivates.
Thank you so much, Sebastian. So I think that as a follow-up, like, what about that as a standard for deployment of, like, if it's 2x the cost, it won't fly, and it's been really hard. I've tried for many months or years even to find a practical use case where Bayesian deep learning has been deployed. I've tried to do it myself. It failed for thousands of hours. And so I'd love to see even a single example of here's a deployed solution in the real world.
Jan, I'm with you there. In a smaller circle, I've thrown this out just as, as a slightly controversial point, right? I say, I'm not aware of any deployed Bayesian deep learning. And the nice thing is somebody always speaks up. I know, I heard somebody at Baidu once deployed this thing. I think interesting, okay. So this just pales in comparison to the deployment successes in ordinary deep learning. However, right, if you can make it work, and if you understand the constraints, and if you can make it deployable, maybe there is a big benefit, right? Right now, I think it's fair to say, maybe there are deployments, surely there are deployments, right? But I think there are no big successes, at least not in industry that I'm aware of at 2 big tech companies. And that's kind of maybe revealing in one sense, or maybe, you know, we have optimized the deep learning tech stack so much in one direction. It's actually healthy that part of the research community should focus on fundamental different approaches. So I think, you know, I'm not trying to be super coherent here, right? I can see both perspectives.
Yeah, I guess in a way this initiative also defends, like, okay, we should just, I mean, that doesn't mean that we shouldn't be spending time understanding all this, no, right? So there is so much value in all this journey, but yeah, it's maybe it just takes time to get there. As a Bayesian, also in my heart, I kind of want to believe that. Yeah.
I can give you a sticker. I still have a few hundred at home.
Right. Okay, so we have time for maybe 1 or 2 more questions. So Alexander is asking, so I'm always very skeptical of all this uncertainty and other newly invented metrics. He says, I think all of them are irrelevant, as in the end, fundamentally, as scientists, isn't our belief of wanting to use Bayesian deep learning in some sense, it is the optimal, and hence isn't the only metric we actually care about generalization. I don't know, Alexander, are you in the call? I'm not sure I got the question, so maybe I didn't read carefully. So you're talking about the metrics?
I think I understood the question.
Okay.
If you want to clarify.
Yeah, do you hear me?
Yeah.
Yeah, so kind of the question is on your last slide when you're talking about, okay, what do we care in the end? I think, at least for me, as a person of science, the only reason why I think Bayesian methods are worth it in anything at all is that in some setting and under a certain assumption, which might be mild or not, given the context, however, Bayesian decision-making is optimal. Yeah. And so in some sense, the only thing that I think we should care about always is basically generalization. And that might mean slightly different things based on applications and context. But isn't that essentially the only thing that we should, in fact, care about, rather than getting better uncertainty or things like that?
Okay, so I mean, reality is complex, right? And the question is, like, if we stay in the, I'm a big fan of decision theory. I think it's, for me, it's a foundation of, you know, building machine learning models and using them to make decisions, right? So I think from a decision theoretic point of view, you're absolutely right. They're beautiful theorems, right? Under some assumptions which are defensible, right? You can say Bayesian rational agent is the optimal way to make decisions, right? And so I think that's, you know, that's a very strong, and a lot of things follows from that, and Definetti theorems and so on. Like a lot of things follows from some basic premises, and it's very satisfying scientifically, right? And I think that's huge value in that. I also very sympathetic to the view that generalization is really the most important quantity. In, you know, under some assumptions, like for example, that you work in the same distribution setting, right? And that is something that we can test, and we have, as a machine learning community, we have hard tests for that and established metrics, and we can hold different models to similar standards, no matter whether they're Bayesian or not. I'm also a fan of that, right? Moreover, there are scoring rules, for example, proper scoring rules, an established framework to assess the accuracy of models, right, in a fair way, in a well-defined, well-understood way. And they have unique decompositions into different quantities of uncertainty, like calibration, refinement, and uncertainty. So there's kind of like very powerful, very general results, how to think about models. Now, in reality, right, we have out-of-distribution settings, very challenging. And that's very hard to proxy with a synthetic task. Right? So if you have out of distribution setting, for example, in a real time series task, and there's really drift in the distribution, right? That's a great setting. You can really benchmark models in this real world setting, right? We did a work where we made artificial out of distribution settings. It's very difficult. Maybe that wasn't the right thing. Maybe that's not representative. Maybe your out of distribution data is very different from my out of distribution data, right? So I think it becomes a lot more challenging what we really care about. But I'm on the basic points, you know, that generalization is really important. And you know, the assumptions, making clear the assumptions coming from decision theory, I'm also really sympathetic to that. So thank you for that question. Yeah, I think we are at time. I have to hop to another meeting, I think, I'm afraid.
Yes. No, thank you so much, Sebastian. This was absolutely great. And yeah, thank you everybody for joining. So there is a mailing list for I Can Believe Some Better for next events. And yeah, again, thank you everybody.